This video explores the role of p-values in normality tests and asks the questions, what is a p-value? And does the p-value change with the number of random samples when sampling from a normal distribution, a symmetrical, and an asymmetrical distribution? The p-value assumes the null hypothesis, or HO, of normality, namely normal distribution, and measures how likely it is that any observation difference between groups is due to chance. That is, the p-value measures the difference between two groups of data, a control group, which is equal to the normal distribution, and the experimental group, the sample group we are evaluating. A p-value greater than 0.05 or 5% suggests that the experimental random sampling is probably normal, whereas a p-value less than 5 is significantly different, and the experimental random sampling is probably not normal. For example, a p-value that is equal to 0.25, where the number of samples is 50, there is a 25% probability that the difference between the normal distribution sampling and the experimental group is due to chance. This Jupyter Notebook explores 4 experiments. In Experiment 1, sampling from a normal distribution shows that the range of p-values does not change with random value sample size ranging from 20 to 5,000. In Experiment 2, the test shows that the p-value distribution from the symmetrical beta distribution becomes increasingly smaller with increasing sample size, and the distribution of p-values becomes asymmetrical. In Experiment 3, we ask at what lambda, or dispersion, does the beta distribution become normal? And finally, in Experiment 4, we'll evaluate a range of dispersion value used to calculate a beta distribution and count the number of successful outcomes with a p-value greater than 0.05. For example, a lambda that's equal to 3 with 1,000 trials, and we sample 1,000 times, produces 0% of the trials with a p-value greater than 0.05. But when we look at a beta distribution with a lambda of 10 and 1,000 trials, and again 1,000 samples, it will produce 30% of the trials with a p-value greater than 0.5. At the bottom of this Jupyter Notebook is a data frame that summarizes the p-values and sample size. Before continuing on to our experiments, I'd like to compare a normal distribution to a beta distribution and see what our normality tests say about it. What I've done is I've created a beta distribution which has a dispersion factor of 10 and will sample 1,000 times, and we'll also create a normal distribution and we'll graphically compare these and look at their p-values. So in red is a normal distribution. This is an unbounded curve and can go on continuously. Here we can see it extending out to about 4 standard deviations in either direction. And we have a beta distribution in blue. They're very similar. If we look at the QQ plots, they both look similar. If we look at the p-value for the normal distribution, it's 0.173. Anything greater than 0.05 would be normal. And the beta also looks normal. But if I run this script multiple times, you'll see that the beta sometimes turns out to be not normal. So here we go. This time with the random sampling, we see that the beta is not normal. Again, less than 0.05. So it turns out that about 70% of the time we'll get a not normal for this beta distribution. And this is largely a result of the random sampling of that beta distribution. Moving on to Experiment 1, we'll do a Monte-Carlo of a normal distribution, and we'll change the sample sizes from 20 to 250, 500, 1,000, 2,500, and 5,000, and we'll see what kind of p-value results we get. Here's where we're calling the normal random values and the plotting. And here's our plot. Here's a box and whisker plot These are the p-values on the vertical axis and the number of samples on the bottom axis. The dashed blue line represents a p-value of 0.05 as a reference. So in all cases, we had some trials that turned out to be not normal while we randomly sampled, even out to 5,000. Most of the data, so in this area here, this is the interquartile range, or 50% of the data, is always in the normal position. And in fact, most of the data is in the normal position. I found it remarkable that it didn't change. I would have thought that all the results would have had p-values greater than 0.05, but I've proven myself wrong here. Now let's do the same experiment for a normal-like symmetrical beta distribution. And again, we'll use the same number of samples in this array. And here's where we designate our beta distribution, where we're generating random values with a alpha and beta shape parameters of 7, which makes it more or less normal-like. And let's take a look at the box and whisker plot. Remarkably, when we look at 20 samples, we have something that looks normal, as we saw in the other plots. But as we increase the number of samples, we see that the box and whisker plot looks more and more asymmetrical. And when we get out to 250, almost all our data are coming out to be not normal. And at 5,000, all of them are not normal. As with above, I find these results quite remarkable as well. For two curves that we saw in the PDFs in the beginning that look the same, and the QQ plot looked very similar, but very different when we look at the range of p-values that we get from our experiment. Let's move on to experiment number 3. At what lambda or dispersion does the beta become normal? Before we move down and look at the plots, I want you to remember this sample set right here, where the samples were 1,000 and most of the trials turned out to be normal. That is, had p-values greater than 0.05. So let's go on down. We're going to look at a beta distribution with a series of lambdas from 3, 8, 9, 10, 15, and 20. Somewhere around 10 is usually where the beta distribution has a standard deviation that's close to a normal distribution. So let's come on down and we'll look at these plots. So when we look at the PDFs, we see that with a lambda of 3, it's very broad. 10 is this dark blue, and 20 is very peaked, but has that bell-shaped. So things greater than about 9 or 10 have a normal-looking distribution. If we look at the QQ plot, we see that the blue lines up fairly linearly, and the red, or our lambda of 3, really deviates from that line, as does the 15 and the 20. So let's look at the p-values associated with these lambdas. At 3, the p-value is 0, so none of the trials worked. At a lambda of 8, everything's less than 0.05. When we get to a lambda of 9, we're greater than 0.05. At 10, we're less than 0.05. At 15, we're greater than 0.05. And at 20, we're greater than 0.05. Since we're sampling random values, we can get different results in our Monte-Carlo each time we run this script. But generally, I found that with lambdas less than or equal to 9, we mainly find p-values less than 0.05. And when they're 10 or greater, we start to see them mainly greater than 0.05. In our fourth and final experiment, I wanted to find out if we ran 1,000 trials with 1,000 samples, what percentage of the trials are successful or have p-values greater than 0.05 for a range of lambdas ranging from 1 to 30. So when I run this, I've selected a few here to look at, and we find that with a lambda of 3, we had 0% of the trials being successful. At 7, it's 3.8. At 9, it's 22.4. At 10, it's 31.9% of the trials being successful. And by the time we get to a lambda of 30, we see that 90.9% of the trials are successful. We'll scroll down a little bit lower, and here we can see what this looks like graphically. So basically, right around a lambda of 6 or 7, we start to see an increase in the number of successful trials, and it starts leveling off around 20 to 30. So from this, I would conclude that the normality test that we're using, as the lambda increases, will find a greater percentage of successful trials being normal. Thanks for watching, like, and subscribe.